Every physical and chemical reaction in a formulated product has a starting line. It happens where two distinct phases meet, the interface. These boundaries exist everywhere in physical pharmacy. We encounter solid-liquid, solid-vapor, and liquid-vapor interfaces continuously. We typically evaluate materials by their bulk properties, measuring things like density or overall solubility. But if a liquid cannot spread across the solid surface, a thermodynamic process known as wetting, those bulk properties are effectively irrelevant. An active pharmaceutical ingredient might be highly soluble on paper, yet if that powder doesn't establish adequate interfacial contact with the fluids in the gastrointestinal tract, it will pass through the human body completely unabsorbed. Interfacial contact determines whether a molecule remains biologically inert or becomes available for systemic absorption. To understand why liquids resist spreading, we must look at the balance of forces. Molecules deep in the bulk of a liquid have neighbors on all sides. Their attractive forces pull equally in every direction, resulting in a net zero force. But molecules right at the surface lack neighbors above them. That imbalance leaves a net inward force, continuously pulling them down into the liquid. Because of this persistent inward pull, the liquid surface contracts, minimizing its total area relative to its volume. We measure this state of contraction as surface tension. The strength of this tension is dictated by the long-range intermolecular forces pulling the molecules together, specifically permanent dipoles, induced dipoles, and London dispersion forces. Water exerts an exceptionally strong inward pull, clocking in at exactly 72.6 millinewtons per meter at standard temperature. This happens strictly because of its dense, highly electronegative hydrogen bonding network. This chart plots surface tension against additive concentration, showing exactly how sensitive that hydrogen bond network is. Notice the sharp, non-linear plunge when we introduce a polar organic impurity like methanol. At a concentration of just 7.5%, methanol drops water's surface tension all the way down to 60.9 millinewtons per meter. Because water molecules are more attracted to each other than to the additive, the hydrophobic regions of the methanol are pushed out of the bulk liquid, causing them to preferentially concentrate right at the interface. Contrast this with an inorganic impurity like sodium chloride. The ionic salt pulls the water molecules tighter into the bulk rather than sitting at the surface, which actually causes the overall surface tension to rise slightly. The surface tension of a liquid is a sensitive thermodynamic balance. Trace impurities can radically shift the inward pull of molecules, changing how the liquid interacts with any contacting phase. Unlike liquids, solid surface molecules are rigidly locked in place. This lack of mobility means they cannot self-level, leaving different crystal faces with varying surface energies across the same particle. To evaluate how well a liquid spreads over these rigid solid surfaces, we measure the contact angle, denoted as theta. This angle is dictated by a tug-of-war between three tension vectors: the solid-vapor interface, the solid-liquid interface, and the liquid-vapor interface. Described by Young's equation, a lower contact angle indicates the solid-vapor energy dominates. The liquid easily spreads, indicating strong wettability. There is a critical mathematical flaw in applying this geometry directly to pharmaceutical powders. The equation assumes an ideal, perfectly flat and smooth testing surface, something raw powders simply do not have. The standard industry workaround is to brute force the geometry. Technicians compress the powder into a tight, flat pill, creating an artificial plane they can drop a liquid onto. But the mechanical process of compaction forces the particles through brittle fracture and plastic deformation. It shatters the crystals, exposing entirely new, high-energy surfaces that skew the true contact angle data. By pressing the powder to measure its surface energy via traditional contact angles, you physically destroy the exact property you are attempting to measure. Another method for characterizing and utilizing these surfaces is adsorption, where molecules accumulate strictly at the boundary layer, entirely distinct from absorption into the bulk material. Formulation scientists rely heavily on this mechanism. By introducing a surface-active agent that adsorbs directly onto powder particles suspended in a liquid, they can keep those particles physically separated, achieving steric stabilization. We also see this applied clinically. Extreme surface area adsorbents, like activated charcoal or carbon black, are administered to trap and bind toxins directly in the gastrointestinal tract, a chemical binding principle that has driven the design of everything from emergency antidotes to military gas masks. This physical adsorption between nonpolar materials is primarily driven by London dispersion forces, weak electrical imbalances creating transient dipoles that operate at an extremely short range of roughly 10 nanometers. By leveraging these exact forces, solid-liquid adsorption transforms passive powder surface area into an active binding mechanism, effectively bridging incompatible phases. At the solid-vapor interface, we can use controlled gas absorption to accurately calculate a powder surface area. This theoretical framework was largely pioneered by physical chemist Irving Langmuir. The methodology involves exposing a clean powder sample to an inert gas at a constant temperature. By incrementally increasing the partial pressure of that gas and monitoring the weight change, we can track exactly how much gas sticks to the surface. This plot illustrates a Langmuir, or type 1 isotherm. Notice how the mass uptake rises sharply at low pressures, but quickly hits a hard, flat plateau. That plateau confirms the surface is completely saturated. It represents monolayer coverage, meaning every accessible binding site on the solid is occupied by exactly one gas molecule. No further increase in pressure will force more gas onto the solid. This graph shows two other common behaviors, type 2 and type 3 isotherms. The type 2 curve corresponds to the widely used BET equation. With a type 2 curve, the gas completes a monolayer but doesn't stop. Driven by strong gas-to-gas interactions, molecules begin stacking on top of one another, transitioning directly into multilayer condensation. A type 3 curve, on the other hand, shows almost no early mass uptake. This reveals an extremely weak affinity between the solid and the vapor, preventing significant adsorption until the pressure is exceptionally high. By fitting experimental data to these isotherms, we obtain a precise mathematical fingerprint of a powder's otherwise invisible surface topography. Extracting surface area from these models reveals a fundamental mathematical paradox. A powder particle does not possess a single absolute surface area. It comes down to fractal geometries. Imagine trying to measure the length of a coastline. If you use a satellite, you get a rough estimate. If you use a 1-foot ruler, you capture every inlet, curve, and boulder, and the calculated distance skyrockets. The exact same logic applies to gases. If you use a small probe molecule like nitrogen, it can slip deep into tiny microscopic indentations. If you use a larger probe like krypton gas, it bridges over those micropores, resulting in a drastically different surface area calculation. In interfacial thermodynamics, the measured dimension of a surface is entirely dependent on the resolution of the molecular probe used to explore it. Water vapor interacts with solid surfaces completely differently than standard probe gases. Instead of providing uniform coverage, water selectively seeks out and binds to the polar regions of a solid. Here we see a specialized water vapor isotherm. The danger arises when a material contains amorphous, non-crystalline regions. Water doesn't just stick to the surface, it absorbs directly into the bulk structure. The first inflection point, Wm, represents initial monolayer coverage. But once moisture crosses the second threshold, marked here as Wf, it behaves identically to free, bulk liquid water. At this stage, water becomes an extreme plasticizer. Because water has a glass transition temperature, or Tg, of roughly minus 138 degrees Celsius, it imparts massive molecular mobility. When these mobile water molecules infiltrate a rigid, glassy lattice, they force the polymer chains apart. The structure collapses, softening into a fluid, rubbery mass. Described by the Gordon-Taylor equation, mixing water into an amorphous solid drastically lowers the total system's glass transition temperature, dragging it down toward room temperature. This creates a severe amplification effect. If a drug powder is only 0.5% amorphous and it absorbs just 0.5% total moisture, that water doesn't spread out evenly. It concentrates entirely in the amorphous regions, creating a highly reactive, localized 50-50 ratio of water to solid. Those trace amounts of absorbed water act as localized thermodynamic catalysts. They rapidly trigger catastrophic chemical degradation and physical collapse across the entire formulation. In extreme cases, this leads to deliquescence. This is an autocatalytic process where an ambient humidity threshold triggers a solid to literally dissolve into the very water vapor it is absorbing. This table compares the relative humidity thresholds of different salts before dissolution is triggered. Potassium sulfate remains entirely stable up to 98% relative humidity. Lithium chloride, however, fails and rapidly begins dissolving at a mere 13%. Characterizing these complex, moisture-sensitive powder surfaces without damaging them requires a much more sophisticated approach than dropping liquid on a pressed pill. The optimal modern solution is inverse gas chromatography, or IGC. In standard gas chromatography, you use a static column to test an unknown gas. IGC reverses the mechanism. The column is packed with unknown pharmaceutical powder, and a known reference gas flows continuously through it. The powder slows probe gases based on specific surface affinities. Calculating precise retention times maps the exact surface energies, bypassing the physical damage of contact angle tests. Mastering these invisible dynamics through precise isotherms and IGC mapping provides the predictive control necessary to ensure the physical stability and therapeutic performance of a drug product.